Scientists have observed a puzzling event related to the Higgs boson, which shows our understanding of the particle may not be correct. They've observed an unexpected decay of the exotic particle that's far beyond the accepted realms of the standard model of physics. These unexpected findings challenge the predictions of the standard model and indicate the possibility of new physics at play. To understand what's been observed, let me briefly explain the concept of Higgs boson and the Higgs mechanism using a daily life analogy. Picture the universe as a vast swimming pool, filled not with water, but an invisible substance called the Higgs field. Now, imagine different types of swimmers in this pool. The first swimmer is a professional, streamlined, and efficient. As they swim, they slice through the water effortlessly, barely interacting with it. This is similar to particles like photons, which don't interact with the Higgs field and hence are massless. Next, think about a casual swimmer, maybe someone who doesn't swim often. They can swim, but they create a lot of splashes and waves, and they find it harder to move through the water. These swimmers are like particles such as electrons and quarks. They interact with the Higgs field, which is why they have mass. Now, imagine an inflatable beach ball in the pool. This ball can't move on its own, and it takes some effort to push it around. So we can think of the beach ball as representing heavier particles, like the W and Z bosons. They interact with the Higgs field a lot, which is why they have a lot of mass. Lastly, imagine the waves that move across the surface of the pool when the swimmers move. These waves are like the Higgs boson. When a particle interacts with the Higgs field, it can create a disturbance or a ripple, like a wave in our pool. That's the Higgs boson, a quantum excitation of the Higgs field. When we discovered the Higgs boson at the Large Hadron Collider, it was like seeing those waves in the pool. It was confirmation that there must be swimmers or particles moving and interacting with the pool, or the Higgs field. Now, the problem is that the Higgs boson doesn't stick around for long. Once it's created in particle collisions, the famed particle lives for a mere less than a trillionth of a billionth of a second, or, more precisely, 1.6 into 10 raised to the power minus 22 seconds. This makes it very challenging to study the particle. It's like the particle is created and destroyed in an instant. So one way that physicists study the properties of such short-lived particles is through their decay modes. This decay can happen in several ways, or modes, and which one occurs depends on the specifics of the conditions. And the unusual event related to the Higgs boson involves its decay into another set of particles. Let's get back to our swimming pool analogy. Let's say our swimming pool wave, or the Higgs boson, becomes too big to sustain. What happens next? It needs to settle down, right? And how does it do that? It breaks up into smaller ripples, or waves. Now, imagine that these smaller waves represent other particles. Depending on the initial size and energy of our big wave, or the Higgs boson, it could break into a pair of smaller identical waves, like a pair of W bosons, Z bosons, or tau leptons. It could even create a mix of waves and tiny bubbles, like a pair of leptons and photons. Now, this is where things become tricky. The decay process of the Higgs boson into two photons is not a straightforward one. Instead, it involves a convoluted mechanism known as a loop, wherein virtual particles temporarily appear and disappear. These virtual particles can include hypothetical particles that have yet to be observed, making their direct detection impossible. Interestingly, this process is not limited to the decay into two photons. It also applies to the decay of the Higgs boson into a photon and a Z boson, which is the focus of the new study. The Z boson is the heavyweight of the standard model, an elementary particle that, along with the W boson, is the carrier of the weak nuclear force. At the Large Hadron Collider, researchers sought to investigate this rare decay process. According to the predictions of the standard model of particle physics, only a tiny fraction, approximately 0.15%, of Higgs bosons should decay into a Z boson and a photon. However, the experimental data gathered from proton-proton collisions conducted at the ATLAS and CMS detectors between 2015 and 2018 paints a different picture. Surprisingly, the data reveals that this decay is occurring in around 6.6% of cases, a significant deviation from the expected value. Both experiments identified the Z boson by observing its subsequent decay into pairs of electrons or muons, and the frequency of these Z boson decays was found to be approximately 6.6%. ATLAS and CMS, the two key experiments at the Large Hadron Collider, employed strategic approaches to maximize the sensitivity in detecting the decay of the Higgs boson into a Z boson and a photon. By focusing on the most common modes of Higgs boson production and utilizing advanced machine learning techniques, they were able to distinguish between signal and background events effectively. As a result, they obtained the first evidence of this decay process. However, it's important to note that the statistical significance of the observation stands at 3.4 standard deviations, slightly below the conventional threshold of 5 standard deviations required to claim a definitive observation. This indicates a small possibility of the findings being a chance occurrence. Nonetheless, the measured signal rate deviates from the predictions of the standard model by 1.9 standard deviations, which makes it a notable result worthy of consideration. The Higgs boson has long been regarded as a cornerstone of the standard model of particle physics. However, these new findings suggest that it may not solely complete the model, but could potentially point towards extensions or modifications. Nevertheless, this study serves as a robust test of the standard model and its predictions. With the ongoing third run of the LHC and the future high-luminosity LHC, scientists anticipate further advancements in precision and the exploration of even rarer Higgs boson decays. These future endeavors hold promise for deeper insights into the fundamental nature of particles and their interactions.